so this is a walkthrough of some different types of statistical analyses that we can do to determine if our data is good and to evaluate our data in a little bit of a better way. So the first one we're going to talk about is what's called standard deviation. So standard deviation tells us how spread out our data is or how clustered our data is. Now, why does that matter? Let me show you. So a small standard deviation, let's say that we have 20 people in a banquet hall, it's a Saturday night, you're told that the average age, mean age is 21. What kind of activity are we thinking is going on? Well, I would be thinking it's a party, right? There's probably a DJ, maybe it's a birthday party. That's what I would picture. Because when we think of this information, this is basically what we think. So the average age of the person of a person at this party is 21. So I'm sort of thinking if we have different ages of people, that it looks something like this. You know, this is the number of people of different ages, and I'm thinking 21 is here, and everybody's around 21. But now you find out this. It's actually a mother-child dinner with fourth graders. So you have a bunch of adults that are 30-ish, and a bunch of children who are 10 to 11 years old. Nobody's actually 21. So in your head, you were picturing this graph. But in reality, it's more like this, right? This is 21. Nobody's 21. Everybody's either in their 30s or they're really young. Yet, the average age, it's not like the average age was changed. It's the average age is 21, but nobody's actually 21. So this is where standard deviation can help us. So let's take a look at some actual numbers. So let's say you had these two sets of numbers, 7 and 13, and then 9.5, 9.5, 10, 10.5, and 10.5. What is the average or mean of each set? Well, it turns out the mean of each of these sets is 10. But if you were asked to evaluate which one of these would be a more reliable result, I think everyone would agree set 2, for two reasons. One, we have more data. That's always a bonus, right? And number two, the data is really clustered. All the numbers are super close to 10. Whereas here, yeah, the average is 10, but these are two kind of distant numbers. So this is something that standard deviation would allow us to see more clearly on a graph, rather than just seeing this graph, set 1, set 2, and they're both at 10. If we add standard deviation error bars to this, we're going to be able to get a better idea of what that average really represents. So this is the formula for standard deviation. It is on the AP formula sheet. It also will have off to the side what each of these things stands for, but let's walk through what each of these variables stands for very quickly. So X with the line over it, this is the mean or the average of your data set. X with the little I, this is your individual data points. This E, that looks really weird, it's the Greek letter sigma, it just means the sum. It just means you're going to add together several things. And N is the size of your sample. So let's walk through how you would do this. So step 1, you have a set of numbers. Step 1, you calculate the mean. Step 2, for each individual data point, this is your Xi's, you're going to subtract the mean from that, and you're going to square the result. This is the step that's time-consuming. And in fact, in real life, if you were doing an experiment and you had, 50 numbers in your set, you would not do this by hand. And you'll see why when we work one out by hand. There's programs that'll do this. There's websites that'll do this. You just plug in your data, and it's going to spit back at you the standard deviation. So you're not actually going to have to do the work by hand. It can be very tedious. Step 3, we're going to add all of that up. So after we do each data point minus the mean squared, we're going to add those all together, and then we're going to divide it by the size of our sample minus 1. And then last but not least, we're going to take the square root of the whole thing. Now, that probably still sounds a little complicated, but let's put it in action, and I think you'll see it's not that bad. So here's our original two numbers, 7 and 13. Step 1, calculate the mean. So the mean is 10. Step 2, we're going to subtract each number minus the mean, square it, and add them together. In other words, we're going to do this. So this is what this would look like. So I would do 7 minus 10 squared, that's my first individual number, plus, and now 13 minus 10 squared, And then I would add all of that together. And if I do that, I'm going to actually get 18 as my answer. Now I'm doing this step by step, and I'm going to show you all my work put together in the end. Step 3, we're going to divide this by our sample size. I said population here, but technically a better word for this would be our sample size. This formula, by the way, is a little different. There's two versions, I should say, of this formula. One is for a sample, which is what we're doing. The other version of this formula is for a population. Like if you were doing something with a population of deer and you couldn't count all of them, but you could count all of the numbers in the population or whatever. So there's two variations of this, but this is the one on the formula sheets. This is what we're sticking with. So that gives us 18. And then we're going to take the square root of the whole thing, and we're going to get 4.2. So let me show you. This is all the work put together. So I have our mean was 10. I took each of my numbers minus the mean. I added that together. And then I took the sample size. There are 2 numbers in my sample, minus 1. And then I take the square root of the whole thing, and I got 4.2. All right, let's take a look at what this looks like for our second set of numbers. So our mean is still 10. We would now subtract each number from the mean, square it, and add them together. That actually is going to give us 1. We're going to divide this by the population size minus 1. We're going to get 0.25. And then we're going to take the square root of that. Here's what the work looks like. Ooh, and it looks like, unfortunately, my screen got cut off. So you guys can't see this down here, but this is over 5 minus 1. Sorry about that. Which gives us the square root of 1/4, which is 0.5. So notice how tedious this is. Imagine if you had 20 numbers. You're not going to want to do this. This is the step. This is the step that takes so long, right? The more numbers you have, the more terms you're going to have to add together. So I took each individual number minus the average, and then divided that by the total number of numbers in my set, 5 minus 1. Okay, so what does this tell us? So if I add, so this is statistics, this is not me. Statistics say that 68% of the data, if you were to count a graph, one standard deviation, 68% of your data should lie within those error bars. So in other words, how do you graph that? So here's my original graph, and I've added error bars to show plus or minus 1 standard deviation. So what I did was I took my standard deviation, it was 4.2, this is from the previous slide, for data set 1, and I go from my average up 4.2, down 4.2, and that is 1 standard deviation, meaning that 68% of my data, should lie within those error bars. So that tells me how spread out my data was. And for my second data set, if you recall, data set B, my standard deviation was 0.5. So that tells me that 68% of my data lies within here. But if you were to graph 2 standard deviations, and you're not ever asked to graph more than 2 standard deviations represents 95% of your data. In other words, statistically, again, I'm not the one that came up with this 68, 95%. This is a standard across the board. If you see a graph and they've drawn error bars for 2 standard deviations, it means that even though you can't see what the raw data was, 98% of the original data falls within those bars, which means, wow, my original data was really spread out. It was as high as, I guess that's going to be like 18 and as low as like 3, right? If I add, and now how do I graph 2? Just to clarify, sorry. My standard deviation was 4.2, so I double it to get 2 standard deviations, and that's 8.4, and I go up by that much, down by that much. So that's showing standard deviation. For the standard deviation of set 2, I took my standard deviation of 0.5 and I double it, and it gets 1. So 98% of this data falls within this little tiny error bar. So you can clearly see, as the reader of the graph, you would know that set B, the data was very clustered. 98% of the data was very, very close, within plus or minus 1 of my mean. But for set A, my data was really spread out. And so this average is not really as meaningful as this average. So that's what standard deviation can tell us. Now, technically, what's a better measure of differences is with something called standard error of the mean. Standard deviation just tells us how spread out our data is. But standard error actually will tell us how confident we are that the average we got is the true average if I repeat the experiment. Let me give you an example to clarify what I mean. So you go to a lake, it has over 10,000 fish. You catch 100 fish and you calculate the average size of a fish. Now I could get the standard deviation of that and it would tell me how spread out my data was, but I can do something more. I haven't tested all 10,000 fish in the lake, so I don't really know if the average size that I got for a fish is accurate, right? Because I could go the next day and test another 100 fish, and I might get a different number, and go the next day and test another 100 fish, and I get another number. Unless I test all 10,000 fish, I'm not going to know what the real exact average size of a fish is, but it's not possible to count all 10,000 fish. So what standard error of the mean is, it gives us something called a confidence level. It's how confident we are that the average we got is the real average. How close do we think we are? If we repeated our experiment, how confident are we would get the same answer? So it's a little different. Now it takes into account two things. The standard deviation, because the more spread out your numbers are, the less confident you're going to be that the real average is there. If my numbers were really spread out, I definitely might get a second different answer the next time. And this got cut off, but the bigger your sample size, the smaller your standard error of the mean is going to be. Because think about it, the closer I get to testing all 10,000 fish, the more confident I would be that the answer I got, the average I got was exactly the correct average. So here's the formula. Standard error, remember x with the line over it is the mean. And all you're doing, it predicts, again, how accurately your data represents a random sample, how confident you are. Two standard errors of the mean means you're 95% confident your real average lies within those bars. This is the formula. It's the standard deviation, which we already just learned how to calculate, over the square root of the sample size. Remember, the sample size is the number of numbers in our sample. So for our original data set, the standard error of the mean is 3. For my second data set, it's 0.3. This is just already calculated for you. In other words, if I had a graph and it had two standard error of the mean bars on it, I would have to go double this. I'd have to go up 6 and down 6, and that would mean that my real average, if I repeat this experiment, I'm 95% confident it should be somewhere within here, which means I'm not all that confident that the average is 10, right? I'm thinking the average could be anywhere in this shaded area. But for my second data set, my standard error is only 0.3. So if I graph two standard errors, I multiply that by 2, I'm only going to go up 0.6 and down 0.6. That means I'm 95% confident if I repeat my experiment, my average should fall within these bars. So it's giving me a confidence level of how certain I am my average falls within that range. The smaller those bars are, the better. And this is important for the AP exam, if two error bars overlap, when you have two standard errors of the mean graphed, it means there's no statistical difference between those two groups. If they don't overlap, it implies there is a statistical difference. Because remember, the true average can be anywhere within those bars. So this is what I got. My real average falls somewhere in here. If I have a second set of data and my bar looks like this, and you're asked, is there a statistical difference between set A and set B? Your answer is no. Because in real life, we don't know. The real average could be anywhere in the shaded area. And these error bars overlap each other. So you would conclude there's no statistical difference between those two groups. So just really quick, here's an example. Oh, by the way, because I'm trying to run out of time on this recording, this can be, error bars can be on a line graph or a bar graph. So just to show you, I was showing you on a bar graph, but on a line graph, you can also add error bars. So just FYI. So really quick, let's look at this. So ethanol and saccharin, is there a statistical difference? So here's ethanol, here's saccharin. So if I was to take this and sort of just draw an invisible line, just shift this over. Notice how it hits this error bar. There's not a statistical difference between those two groups. Saccharin and salt, same thing. The error bars touch. They'll hit each other. If I slide the error bar over, it hits this one. No difference. Ethanol and salt, this and this, yes, statistical difference. If I slide this error bar over or slide this error bar over, notice I end up still with a gap between the two. So yes, statistical difference. Salt and sucrose, same, right? If I slide this error bar over, this one has a statistical difference basically from all the other groups. So yes. And salt and water, no statistical difference because these error bars hit each other. All right, so that's it. That's standard error. and the difference between standard error and standard deviation.